All right, let's start out with what this program is like. Nothing to it, right? We just press a button, the computer designs the antenna for us, and we're off working DX with our 60 foot square yard with a 160 meter DX antenna. Of course, we all know, or I hope we all know, that it's not like that at all. What the program really does is it's an analysis program, not a design program. It doesn't design antennas for you. What it does, you design an antenna and it tells you what the antenna will do. Now, this can be a really important part of a design process where it's an iterative process. You try a design, you see what the result is, and you like it or don't like it, and you perfect the design. And there are programs that will do some of this automatically for you and do the optimization, one of which is AutoEZ. You can find information on that program on my main website, EZNEC.com. It's a very capable program, and it will actually go through the iterations for you to optimize designs. Basically, what EZNEC by itself will do is you describe the antenna to the program by telling it where the wires are in space. All antennas modeled with EZNEC composed of straight wire segments. And you can make multiple segments, short, long, and you'll get some examples here where we've got things like a helix made from line segments. You can make loops the same way, for example. You put sources in the antenna wherever you want. You can put in loads, which consist of resistive, inductive, capacitive elements, transformers, L networks. You can model pretty complex, complete systems with EZNEC so that you can evaluate how well a phase shift network, for example, is working, or how well you're distributing the current to the various elements of an array. You can put in non-radiating transmission lines, which you can include loss with that if you want, and ground. And then the program will tell you the gain front to back ratio, pattern comparison, source impedances, SWR, load dissipation, currents, and so forth. It's really great for modeling interaction with other antennas and conductors. And you can easily compare antennas with EZNEC. Richie mentioned the FCC RF exposure requirements, and I believe that FCC accepts EZNEC results for evaluating the fields that are produced by an antenna. When you do try to do the near field analysis with EZNEC, you'll see a disclaimer saying that EZNEC can't be used for determining human safety. And that means that whatever you see with EZNEC, it's not telling you whether it's safe or not. And there's also a realistic factor, and that is that I would guarantee that if you took the best professional measurement equipment and skilled technicians to come and measure field strengths in a house or an urban environment, you would have easily results that differ by several dB. And these results are way tougher to make than you would ever think. I use as an example the proof of performance measurements that are done by for AM broadcast stations. And here we're talking about relatively low frequencies, long wavelengths, which are relatively easy to measure with pretty good accuracy. And the AM stations have to do a proof of performance periodically, where they, at least the ones with the antenna pattern with multiple elements, and they have to measure the field strengths at various distances and azimuths relative to the antenna. And I defy you to find a professional engineer that does these measurements that will attempt to do a proof of performance without knowing in advance what the results should be. You won't find one, simply because the results can easily vary, again, several dB by simply standing a couple of feet in a different spot, or maybe putting the antenna between you and another tower, or many different variables. By using straight pieces of wire, you can build very complex antennas if you want with EZNEC. I've got just a few examples here. And down at the bottom, I say not slinky antenna. The fact that slinky antenna just requires too many little short line segments generally for EZNEC to handle. Plus, there are some issues with having the turns really, really close together. It can't handle patch antennas or microstrip antennas because there's dielectric between the two elements of the antenna, and EZNEC does not have any way of accommodating a dielectric in the model. Horn antennas, you can build a wire grid model of a horn antenna. It's probably not terribly practical to do. And likewise, a parabolic reflector. And the reason I put parabolic reflector there as one that isn't too suitable is that you can build a wire grid model of a parabolic reflector, but people who design parabolic reflectors are not usually too interested in the gain and the main lobe. Those are pretty easy to calculate. What they're really interested in is the side lobes and the minor lobes. And the wire grid model being an imperfect model of the parabolic reflector, you'll probably not get really good results, realistic results of the more subtle features of the pattern from EZNEC. Okay, how does it do it? Why, with the wizardry, of course, but not really. There really is a man behind the curtain who's turning all the knobs and wheels and stuff. And it's a very smart man. It's not me, by the way. EZNEC does its magic with physics and mathematics. It uses a code called NEC2 for calculations. I do sell one professional program that uses NEC4, but it's very expensive. Plus you have to buy a license for NEC4 before you get it. So the total cost is beyond that of most hams, although some hams have bought it. But NEC2 is public domain. It was written in the 70s. And it was made to run on the mainframe computers of the day. It's a very advanced program, and it uses the basic fundamental laws of physics that dictate antenna operation. So if you can make a model that successfully imitates a real antenna, you'll find that the results are breathtakingly accurate. The differences between a model and a real antenna are due almost exclusively to the ways in which the antenna differs from the model. And in an urban environment, I'm looking here through the window at my couple of dipoles up there, strung among trees. And in my models, I have accounted for various bends and so forth, and the dipoles have pretty broad patterns. So I have quite good confidence in the patterns that I see for those. But there are a lot of cases where it's virtually impossible to completely imitate the environment of an antenna. You can include things like rain gutters and so forth, but you have to know what size and position they are in order to tell the program, and a lot of times you don't know that. So I'll try to explain a little bit about how EZNEC does what it does. By the way, I did not write NEC2. I did not have any part in it. What I wrote was an interface. NEC2 was really written for the computers of the day to take input from punch cards and output to a line printer, literally. And it's written in Fortran. It's a very complicated program. And what I wrote was an interface, making it usable for people with modern computers. I also made it go a lot faster and added quite a few features that weren't in the original program. But I didn't write the calculations, the code that does the actual calculations of the antenna performance. My contribution, my interface is a mere 70,000 lines of code last I counted, and I wrote every one of them. Here is people, I've been asked from time to time, can you explain how EZNEC does the calculations? People kind of think it's something like a complicated form of, or an advanced form of 492 over F or something. And this is one of the pages out of the NEC2 manual, which, by the way, those of you who are suckers for punishment can download this from the web. It's a public domain. This is one of 87 pages explaining the mathematics behind how NEC2 does the calculations. So let's start with the first law of computer data laundering. Oh. And that is garbage in, garbage out, gospel out. People do that. They put the numbers in the program, and then what comes out is supposedly gospel, and believe it. And certainly the output is not really any better than the information you put in. If you ignore certain important characteristics of the antenna in your model, then the output, of course, won't represent what the real model does, or what the real antenna does, excuse me. And so computers don't do what you want them to do, they do what you tell them to do. And those are things to keep in mind when doing modeling. And similarly, keep in mind that antenna analysis programs don't analyze your antenna, they analyze a model of your antenna. And again, if the two are really very similar, then the results will be similar to that of the real antenna, otherwise no. Let me give you a very quick example. I'm not going to do this much longer. I just wanted to give you a little background for the people who are absolutely new to modeling. Those of you who have been using EZNEC, feel free to take a little nap here, but it won't be much longer. What we've got here is a 1.5 volt battery, 3 ohm resistor, and we calculate V over R and find it's a 1/2 amp, and that's really cool. And then we go to measure it with a meter, and we find that we're 27% low. Well, that's not too awfully hot, especially for such a simple model of 2 components. And so why did that happen? Well, at first we find out that the resistor isn't really 3 ohms, it's really 3.2 ohms. It's within its 10% tolerance. And the battery has got a 1/2 ohm of internal resistance, which isn't in our model. And the actual cell voltage is not 1.5 volts, it's 1.35 volts. So if we put these in our model, then we will get the correct answer. But again, you know, here we've got the real system, and here we've got the model, and the two being different, the results are being different. Now you can imagine what might happen if we took a gigahertz signal generator with a 1.5 volt RMS and hooked it through some kind of long wires to a resistor of 3 ohms. We wouldn't get anything near our 1/2 amp. We now have to add quite a number of other things to our model in order to make this work. We'd have inductance and capacitance involved here that weren't in the DC case. So those are just some examples on how things can go awry doing modeling if you're not careful. Now at this point, I'm going to attempt to get over to EZNEC. Okay, this is what you'll see when you start up EZNEC. It's just a small screen. People ask, gee, why can't I make it cover the whole screen? And my response is, why do you want it to cover the whole screen? It's a Windows-based program, and there are lots of windows that open up, and you don't want them covering each other up. There are another few things about EZNEC I want to point out right up front, which I think some EZNEC users don't really understand, and it would be good to understand. First of all, there's a very complete manual, and the manual is always available. You don't need to, you can get a printed manual. Download it from the web, or if you get the CD, it's on the CD, but you don't need it. And I think you'll find once you get used to using the online manual, or I should say the integral manual, it doesn't have anything to do with the internet. The integral manual, you will not go back to a printed one. So the way you access the manual is you click Help right there, and Contents, and there is the manual. Here's the manual, 200 and some pages. Beautiful. It's very complete. And the way I tell people to start out is under this Getting Started. There are some just general tips. And for people who have upgraded from a different version, it shows what's new and so forth. And then the place where I really recommend everybody start is Test Drive. And what the Test Drive is a step-by-step list of instructions on how to create a model with EZNEC and how to use some of the features it has. And this gives you an idea of how the program works and how you use it. If you don't go through this, you may be quite lost. It's perhaps not intuitive, depending on what you're expecting. It might not be what you're expecting. And it goes on and gets more advanced. In the later ones, I got to where I was putting in more figures and illustrations on what's going on. This is an example of how to use the L network item in the program. And then clear down to the end, I've got an example of how to model this roof. This is a peaked roof, which is a wire grid model, what we call a wire grid model for modeling like plates of metal. You can model cars and other solid objects that way. And this takes you through step by step how to model this roof with only entering the coordinates of one wire, because EZNEC requires that you have coordinates of each wire in X, Y, Z. You have a wire here, here's the X, Y, and Z coordinates, and X, Y, and Z coordinates. People get intimidated by this and think, boy, that's really complicated and complex. And I show how, by using the various features in EZNEC, you can build this whole model with only entering the coordinates of one wire. You have one wire to start with. And all this rest of this stuff is done by replicating. You can duplicate wires, you can rotate them, you can reflect them, you can do lots of stuff to build these complex models without really hardly ever entering a coordinate. There's a lot of detail on how to build models. If you've got questions about what about ground? Ground is kind of complicated. That's all explained in the manual. There's also an index. It's a very complete index. As you can see, there's that much stuff in the index. And if you go to any of these terms, you look at absolute versus relative value of the source, and there you've got it. Some of these have more than one choice if you select it. Sine, file, side lobe, so forth. All right. So this is all in the manual, and make sure you make use of it. And then you can also search the whole manual for any term appearing anywhere, any word appearing anywhere in the manual. And there's where dipole appears in all these topics right here. So it's very powerful. Also, there are a lot of hyperlinks. Go back to the Contents tab, and there are hyperlinks. Let's see if I can find some in here. Okay, here's some. Like here's a hyperlink for action button. You don't know what an action button is. You just click that and it'll tell you what an action button is. You can go back to where you were and continue on, or you can leave that other one open and so forth. So there's the manual. One other thing is, I just had the wires window open here, is context sensitive help. A lot of people don't realize that EZNEC has got context sensitive help. What you do with the context sensitive help is you make sure that the window you're wondering about is the active window. That is, right now, the main window here is the active window. I click this once and it becomes the active window. That is, any text you type will go in this window and so forth. Once it's the active window, then you just press F1 on your keyboard and it opens up the manual to the section that describes that window and all the things in the window and how to use it. So there are all the things about the wires window that you might wonder about. And that's something that I think a lot of people aren't too aware of. By the way, the EZNEC, there is a demo version of the program that's available. It's free. You can get it at EZNEC.com. And it is exactly like the standard program in all ways, except you're limited to how complex an antenna you can model with it. You can model simple antennas up to maybe a two-element Yagi, if it's fairly simple one, a two-element quad. You can get a reasonably good model of. With the demo program, there's no time limit on it. If you want to use it for the rest of your life, you do so with my blessing. I'm very pleased that you use the demo program if that's all you need. And so that's a good way to start. And another really cool thing about the demo program is you can get it to find out whether it's really something that you really like or want to use. And if you don't, then you just don't use it anymore and you don't buy the real program. But if you do buy the real program and you don't like it for any reason or no reason at all, let me know and I'll immediately refund the full purchase price. That's always been my guarantee. There are very few people who have done that. I had one guy contact me and he said, I got EZNEC about 20 years ago and I never used it. And I said, okay. And I sent him I sent him a check for what he paid for it. There's no time limit on that. Okay. Any questions so far? Okay, I'm not seeing any. Maybe, I don't know if that means there aren't any or, or there's something I've done here that, or haven't done. Okay, I just want to give you here a couple of examples of antennas that I've modeled with EZNEC. This one right here. Get it up to where you can see it. We turn off some of the extraneous stuff that we don't need for this. Turn off the segmentation dots and the wire numbers so we can see the wires. Okay. That I built, and again, I entered very few wire coordinates. What we've got here is a vertical antenna, which is top loaded, and it's also bottom loaded with this. This is all created on or built on a piece of PC board-like material. It's a Rogers material. It's got a lot of better characteristics, but it's basically a PC board type material with printed lines on it. And so it's all planar. And I had to make a fairly low frequency vertical. And so I top loaded it and I bottom loaded it. And then I had another antenna over here, which was on a different frequency that I had to make to not interfere very much with the other antenna. They had to be fairly independent. This line here is the transmission line going up to that dipole, and it's not connected right at the moment for an analysis. This was a design I did as a consulting job. It goes into it went into a winglet of a drone. And so that's an example of by the way, this is not a final design, so I'm not revealing any secrets, and it was done many years ago, and I'm not going to tell you who I did it for. But this is an example of the kind of complex antenna that you can do with EZNEC. This mess over here, this is a box that contained a metal box, which contains some electronics, which had to be part of the program because it's really important in determining the pattern of the antenna. So that's one. And I'll just show you one other. This was another consulting job that I did. This was a preliminary thing I did. This is not the final design, but this is 4 helix antennas that are all driven in a particular way and phased with a ground plane. And that was done with EZNEC. And these helical turns here are made out of wire segments. They are the straight wire segments that I mentioned that EZNEC was restricted to. Let's go view, and I'll show the segmentation dots. There you can see the dots where the segments, which show the boundaries of the segment. So there's one segment, there's another segment. All wires are broken up into straight line segments. And what the program actually does, what NAC2 does, is it calculates, first of all, the self and mutual impedances of every pair of segments. So it does millions of calculations to compute that. Then it takes the sources, the voltages of the sources. Then it does this giant matrix Ohm's law calculation to figure out what the currents are in each segment. And then finally, it calculates the pattern by adding up the fields from each segment. And the standard EZNEC program allows up to 500 segments. The EZNEC Plus allows up to 2,000 segments. My professional programs allow up to 45,000 segments. And let's see how many in this one. This one has got 1,882, so you could model this with the EZNEC Plus. The demo program is limited to 20 segments. That's the only difference between it and the standard program. Okay, so those are just a couple examples of the sorts of things that you can model with EZNEC. I'm going to now do just a really quick little example of the kinds of things, one of the kinds of things that you can do with EZNEC as far as learning a little bit about antennas. So what I'm going to do is I'm going to start by opening a model, which is one of the example models that's sent with EZNEC. And it comes with EZNEC, and that's BY dipole. That's a backyard dipole. And we'll take a look at that, what that looks like. It's just the green wire there, the greenish wire is the dipole. And the little red circle in there is the source. So it's like a dipole with a magic transmitter sitting right in the middle of it. So it's really idealized. I haven't accounted for any radiating feed line, for example, which can be really significant. You can model that with EZNEC in cases where it is significant. Like if you tied a coax cable to this antenna and put it down, then with no balun up there or no common mode choke, the coax would become part of the antenna and would radiate, and we can model that with EZNEC. And if you have that situation, you would have to have that as part of the model, or the results you get from EZNEC wouldn't represent the real antenna. I think I could probably do a whole hour session on modeling ground with EZNEC. That's really the weak point of EZNEC, the ground models. But in most cases, it isn't terribly important, and it's good enough. So I'm going to change this without any comment for the illustration I'm going to make here. Now what I'm going to do is I'm going to model a dipole up 1/4 wavelength. And I'm going to start by opening the wires window here. I've got, by the way, I've selected units. You can select units in feet, or you can select them in meters if you want, or you can select them in wavelengths. And this is 20 meters, 14 megahertz. I'm going to go down to 40 meters. We'll just go to 7 megahertz. And I'm going to rescale the antenna. And what that's going to do is it's going to make it twice as long and twice as high, so that actually the results will be the same from EZNEC in terms of the pattern, shape, and gain, and so forth, with the exception that ground will act quite the same at the two frequencies. So now I've got a dipole. It's up 66 feet. Now I want to put this up 1/4 wavelength for this illustration. So what I'm going to do to make things simple is I'm going to change the units to wavelengths. And now I've, down here in the wires window, I've got that the height, the Z coordinate is the height above ground, is about 0.42 wavelengths right now. So I'm going to change the antenna height. And there are a couple of ways I can do it. One way is I can change height by, and that way I'd have to subtract some off, and that's just kind of a pain. So I'm just going to change the Z coordinates of that. I'm going to change it to 0.25. And you'll see when I hit enter, one side has gone down to 1/4 wavelength. And now I'll take the other side and go 0.25 and enter. And now it's down to 1/4 wavelength. You can see here the Z coordinate, which is the height, is 1/4 wavelength. So now I've got a dipole, which is 1/4 wavelength above ground. And I'm going to just do a pattern of this. This is over, let me change the ground description to typical ground. This right now is kind of a, this one is a very good pastoral rich kind of ground in this model. I'm going to change it to average ground here. Just change it to average ground. Now the ground conductivity and dielectric constant are that of average ground. Now finally, I'm going to choose what kind of plot I'm going to have. I'm going to do an elevation plot, which is done down here in the main window. And I'm going to do it at an azimuth angle of 0 degrees, which is the plus x-axis. And I'm going to do a 2D plot. And there's what the pattern looks like. And I'm going to make sure it's easy to accidentally be showing the pattern at right angles from where you think you're showing it. So in the view objects, I'm going to have it show the pattern right on the same display as the view antenna. And so now we see that the pattern is, sure enough, we're looking at broadside. We're looking at the elevation pattern broadside. Now, some people kind of get confused about really what a pattern means. They kind of think it means something about, you can superimpose a pattern on a map, say, and here's the signals here and it's not there and so forth. Let me explain what this pattern means. It's a polar plot. And imagine that we've got a little man or woman, let's be fair about this, that's out a long distance away from the antenna. It doesn't matter really what the distance is, except for it's quite a ways away. So the person has a field strength meter, and the person starts out at ground level with this meter and measures the field strength. And in this case, it will show that the field strength is 0 right at ground level. If we look down here on the lower right-hand side of the display, we see this cursor elevation is 0 degrees, and the gain is minus 99.99 dBi. That's as close as EZNEC comes to 0. And so there's no field strength from that antenna completely at the horizon. And then the person goes up vertically, staying the same distance away from the antenna. The person goes up a bit vertically, goes up to say 5 degrees and measures it again, and they measure minus 0.9.37 dBi. And they go up and they continue going around, up and overhead, and then back behind the antenna, so that they're doing this whole loop, but staying the same distance away from the antenna the whole time, and measuring the field strength. And then we come and we just plot those field strengths on our graph here. And so now we have a graph of field strength versus distance. Field strength versus elevation angle. We can do the same thing horizontally. We can look at a horizontal plot by just going here to go to plot type, azimuth, going bang, and then doing a, okay. And I told it that I wanted it at an elevation angle of 0 degrees, and it tells me there's no skywave far field at 0 degrees, which we just saw. So let's go up to, I don't know, 20 degrees or something. 20 degrees above the horizon, we find that the pattern looks like this. And there's what it looks like on the plot here. You see it's tilted up 20 degrees. So we're looking at the plot up 20 degrees from the horizon. And we know this, in this case, the magic person stays up 20 degrees above the horizon and goes all around the compass, completely around the antenna, staying the same distance away and 20 degrees up. And that's how we generate the horizontal plot. But right now I want to show you that, go back to the vertical plot. So we'll go back to elevation. Well, while I'm doing this, I might as well show one more thing, which I will. And that is we can choose a 3D plot. Excuse me. And I'm going to go to 1 degree. So it looks a little better. And I go 3D plot, and that is so dense that we can't really tell much about it. Maybe I shouldn't have gone clear to 1 degree. But the cool thing we can do here is we can look at a single azimuth slate. You see that red line around there? And we can change the elevation angle of that. And we can show that in the 2D display. And we can see it also on the view antenna display. Sorry about that. Hello. Huh. All right. Okay. So we've got this, and we can go to an elevation slice instead, and we can see what happens as we rotate the slice around in various directions. We can see off the end, see what's happening off the end here. And then back to broadside. Okay. You find that very useful a lot of times with complex antenna displays to figure out really what's going on there. Now, back to the elevation plot and 0 degree azimuth. That's the one we had. Now you can see this is a classic cloud burner. It's radiating mostly straight up. There's a term called takeoff angle, which I really hate to use, which is often used for this kind of stuff. And the problem with using the term takeoff angle is that it kind of implies that all of the radiation is going in one direction, which by takeoff. But as you can see, we've got significant radiation down at lower angles. And let's see if I can turn on my data lines right here. Here's some data lines, which in this case are showing the 3D, these magenta ones are showing the 3 dB points. So you can see it's the beam width is 130 degrees. So there's a 130 degree range here where the intensity, the strength of the signal is within 3 dB of where it is straight up. So it's really not so bad as you might think. Okay, I'm going to save this. And I'm going to save this one here as dipole. Okay. Now, let's take and try a vertical. Let's see what a vertical looks like. No. Yes, I think I will after all. It's called BY dipole 1. Okay, now we will open another one of the example models in EZNEC, which is Vert1. And that is a 40 meter vertical. You can't even see it there. It lies right on the axis. It's this black line right on the axis, and you can see the source right at the base. And again, I'm not going to take time in this talk and talk about the different ground models. I'm using an a mini neck ground model here. And what this does is this assumes that the ground is perfect when we do the calculations of the currents and impedances, but then it uses the actual ground characteristics when we calculate the pattern. And the end result is that this is what you would see if you had a perfect ground system, a lossless ground system. A lot of people think that changing your ground radial system underneath a vertical is going to change your pattern. It will bring down your radiation angle, for example. And I can show with EZNEC that that isn't the case. I don't think I'll have time to do so today. But you can try it yourself. Any of you who've got EZNEC, you can try changing the radials and see what happens to the elevation pattern. And you'll find that it makes virtually no difference with the exception of very, very high angle signals. And the reason is that the vertical radiation pattern is caused by the interference between a ray going from the antenna straight up, like my cursor is going here, it's going directly to, let's say 30 degrees, 30 degrees above the horizon. This is going up at an angle of 30 degrees. And also it's radiating in all directions. And the one that's going down at 30 degrees like that is going to hit the ground and bounce off, and it's going to go up at 30 degrees right in parallel with this one that came directly off. So these two, both the direct ray and the reflected ray at a far distance, interfere with each other, and they add vectorially. And this can result in them completely adding to double the field strength. They can completely cancel if they happen to be out of phase in the same amplitude. And so you'll have a complete null, or they can be anywhere in between. And the nature of the reflected signal, first of all, one thing is that, of course, this path is longer, so you'll get a phase shift because of that. But you also get a phase shift because you also get both a phase shift and an amplitude change because the ground isn't perfect. Only if the ground is perfect will you have this complete reflection. But EZNEC takes into account the imperfect ground. And so you'll find if you do, we might have time to do that, do some vertical over various kinds of qualities of ground, and you'll find a great difference. The low angle that the vertical antenna has over perfect ground is kind of disappears when you do it over real ground. And what we've got here is we've got the same kind of ground we had before in the last example with the dipole. We've got average ground. We've got 40 meters. And so we're going to see what the elevation pattern looks like here. We got plot type elevation. And so it looks like that. You say, oh boy, That's not a cloud warmer. That's got an elevation angle, takeoff angle, if you will, maximum signal at 26 degrees above the horizon. You notice it at the horizon itself, again, you got 0. So here's a vertical antenna. You see the pattern sometimes of vertical antenna over perfect ground. I'll do that briefly here. I'll change this ground type. Oh, I'll do that in a minute. Let me do this first. Anyway, we say, boy, that's way better than the low dipole, right? We all know that a vertical's got a lower takeoff angle than a low dipole, quarter wavelength dipole. But let's see, let's take the, oh, I'm going to save this one here. I'll save this as vertical. Let's call it vertical real ground. Okay, I would just save that plot. Now what I'm going to do is I'm going to superimpose. Now, one thing to point out is that the default, you can set this outer ring for a fixed value, but by default, if you don't specifically set it, what EZNEC will do is it will always make the strongest part of a pattern be at the outer line. So even if antennas have vastly different gains, they will still extend to the outermost part of the pattern. So what I'm going to do is I'm going to put the dipole trace on top of this one, but now they're going to be scaled the same as each other. So let's see what happens. Now here's our quarter wavelength high dipole right here. And here is our vertical antenna, which has got no loss in the ground system. We've got essentially an infinite number of radials underneath it. If we had a real ground system, this whole pattern, the shape wouldn't change hardly at all, but it would be smaller because of the loss in the ground system. I didn't finish explaining why changing the ground system doesn't change the pattern. The fact is that at any moderate, even moderate radiation elevation angle, the reflection from the ground that is causing the pattern is taking place way beyond any reasonable size radial system. It's typically many wavelengths away. So it doesn't affect the shape of the pattern. So anyway, this is a lesson here. Let's get some numbers here, which we can do. We can take a look and see how our antenna is compared to the dipole. And it turns out that right here, let's try 26 degrees. That's where it was the highest. And I got to change here, just one moment. I'll switch over here so we got the cursor on the other trace. Now we're at 26 degrees, and way down here at the bottom of the data window, it shows that we're 3.28 dB between these two. So the dipole is 3 dB stronger than the vertical, even at the elevation angle where the vertical is the strongest. And the dipole beats out the vertical clear down to 14 degrees. Below 14 degrees, there's looks like 1 dB, 2, 3. Way down here, there's about a 3 or 4 dB difference. Both of them are way down there. In this range right here, I'm looking at these numbers down here, 2.21 dB difference right there, and so forth. So that's the kind of thing that you can illustrate with EZNEC very easily and answer a lot of questions you might have about how antennas work. Let me do one more quick one here. I'm going to take and remove the dipole trace. I've got that one with real ground. I'm going to take and change the ground type to perfect. You've probably seen this plot before and you think that's the plot of a vertical. Well, no, that's not the plot of a vertical. That's a plot of a vertical with perfect ground. And that means the ground is perfect clear on out where the reflections are taking place. And in order to get these low angles, the reflection is taking place a very long distance from the dipole. And I'm going to save that one. Save trace as vertical perfect. Perfect ground. Okay, now let's do just one more. Let's try saltwater. Okay. Go over here to ground. Saltwater right there. Okay, guys, you guys have got a boat. You live on an island, right? Long Island, you must all have boats. If you got boats, that's what you ought to do, is make yourself a vertical antenna, because you can see what happens with salt water. I'm going to superimpose those two other traces here. I'm going to put on the vertical perfect ground. Look at that. There's hardly any difference. Here's the perfect ground is the blue one, and the salt water is the black one. And now let's take our real ground, average ground. We're going to add trace. We're going to add real ground. And there's what real ground does to our dipole pattern. We've lost our low angle radiation pretty completely. It's way, way down anyway. And even where it's best, it's still a good 5 dB, well, good 3 dB below the perfect. So those are some examples of things that you can do with EZNEC to illustrate antenna principles. You can do a lot of other things like evaluating what happens when you connect your coax directly to a dipole. You can see the currents in the feed lines, that the feed line is radiating. You can see how that affects the pattern. You can see how you get interaction between antennas, many, many things like that. Let's see, there was one other model I was going to show you, and that is this one. This is modeling a field day setup where I've got this is my field day special antenna. I had put that in QST many years ago. It's a 2-element array made out of twin lead. Very lightweight, because for many years we backpacked up. Those days, I'm afraid, are kind of probably over now. But it was sure a lot of fun for 30 years or so. I'm going to turn off the segment dots again so you can see what it looks like. There are a lot of extra things in the model here to deal with the twin lead and its dielectric. And let's see if I can zoom here. I'm sorry, this is another field day special. This is 20 meter field day special. And what I've got under here is an element for 15 meters. It's a 2-element inverted V Yagi. And then I've got a matching arrangement at the feed point so that it matches both antennas. I can do the whole thing with one feed line. And got a nice directional pattern on both 40 and 15 that covers most of the US from here on the West Coast. This is just a 3-band trap dipole that I use for the other direction. I've got these facing basically east to cover most of the US, and then this is north and south, and that I can use to pick up California mainly. So I think I've used up my hour, and I'll be happy to answer any questions, time permitting. Let me see if I can get, let's see, I'll see if I can get back to my screen. Well, I guess I can just share this with you. That's Prospect, Oregon there. It's a nice little spot along the Rogue River I flew into. That's my airplane there. And a couple of deer. It's a really nice spot.
If you roll the mouse all the way up to the top, you can get to the stop sharing button.
Okay. There we go. I'm back.
Okay.
Are you guys back?
Yes.
Okay. Any questions I can answer? Uh-oh, that's not a good sign. No questions.
Well, Roy, actually, I had one. I was just holding off. I've used the demo version, as well as I've also used like 4NEC2 and MMNA and GAL. And the vertical discussion you were just talking about, one of the things I always understood was that I thought only NEC4 was capable of modeling like ground radials on a vertical antenna. I guess I'm mistaken on that. Is that correct?
Yes and no. First of all, that model that I had does not have any radials involved. It is a ground that is considered that's perfect when it does the calculations of impedance and the impedances and the currents in the antenna. So it imitates a perfect ground system. If you want to model radials, what you can't do with NEC2 that you can do with NEC4 is model buried conductors. You can't model buried conductors with any of these programs. The only way you can model buried conductors is with NEC4 and recently introduced NEC5. And those both require you to buy a license from Lawrence Livermore in order to use. What you can do to get a reasonable approximation of buried radials is you can model the radials as wires that are just above the surface of the ground. And that's explained in the EZNEC manual. If you look up radials, I believe probably in the index, you'll find it.
Right, which is what I've done in the past. I've modeled about 2 inches over the ground. I've been told that that's a reasonable approximation, or about as good as you're going to be able to get with
Yes.
NEC2. And I guess my next question would be, how much difference? I believe it's a nominal, very insignificant difference. Is that correct?
Usually that's correct. You'll find that when you get somewhere around even 4 radials, typically you're talking about maybe 3 dB of loss, 3 or 4 dB in that general ballpark. By the time you get 16 radials, you're maybe down to 1 or 2 dB of loss. And so, you know, if you miss a bit with the amount of loss in the radial system, it won't really make that much difference in the overall performance of the antenna. And again, it doesn't make really any difference in the pattern unless you're doing NVIS stuff. You're interested in what's happening at an elevation angle of 65 degrees or 90 degrees or something.
Great, thanks a lot. A really terrific presentation. I could sit here and pick your brain for hours, but I won't. But thank you very much.
Well, thank you.
Roy, this is Mike, WY2U. I have a question on something that you did not cover tonight, if I could.
Sure.
Okay, I know you, well, first of all, I use the EZNEC 6 Plus, and I've enjoyed it. I've been using it now for several years. I have all the updates. I like to use antennas that employ loading devices. Now, one thing that is of concern to me is calculating the losses of loading. And you do that very nicely because you can calculate single element loads like an inductor or a capacitor. Do you have any way to recommend how you would calculate losses in an L network, because that isn't part of your main menu?
Well, an L network certainly is, but the losses, you know, now that you mentioned it, I don't think so. I don't think it reports the loss. It doesn't report the losses.
No, it does not. You can model them, but you can't report the losses.
You know, you're the first person that's asked me that.
I am.
Believe it or not, thousands of people use EZNEC.
That would really be something handy if that's not too difficult to do.
Thank you. I will put that on my list.
Beautiful. Great.
That's
it really, because again, I've used your program for several years, modeled many antennas, and quite honestly, what you end up with, if you do it right, is very close to what you get when you do some kind of measurements on it. So congratulations on your fine program. Really enjoy it.
Let me tell you something you can do to get at the loss, though, in the L network is what you can do. Of course, an L network which has no resistance in it, which is a lossless inductor, will have no loss. And so it's all in the resistance in the L network.
Well, I'm interested in voltages across the elements too.
Yeah, but in the model, the only source of loss is going to be the resistor.
I agree. But
resistor.
how about voltage breakdown? That's something else I'm interested in.
Okay, that, again, that also is not something, it won't show you the voltage across the elements. And so I can't help you there. But as far as the loss goes, what you can do is you can look at the field strength from your antenna and then change the resistor to 0 ohms and check it again. And the difference is the loss in the L network. Or you can use the average gain feature. That's the other way of getting at it.
Okay.
So that's a workaround for now.
Yeah, but again, I'm really interested in not only power loss or dB loss, it's voltage breakdown in the capacitor and whatever, you know, because that could be significant with some very high Q antennas.
Yes. If you want to know the voltage okay, I'll leave it at that for now.
Okay.
Sometimes you can measure voltage and current in various parts of the circuit by adding a 0 volt voltage source, and then the source data will tell you the current through it. So you can measure the current at one point, any point in the wire, with by putting in a voltage source that is 0 volts.
Oh, that's an interesting idea.
And likewise, you can put in a current source with 0 current across something. Now that has infinite impedance, so you can't put it in series, but you put it across something to measure the voltage across something.
That's an interesting idea.
Yeah, so those are,
Okay.
fiddle.
Yeah, yeah. All right, thank you very much. That's good.
You bet.
How significant is the difference between salt water and fresh water?
And fresh water, I think, probably varies all over the map because it can have very small amounts of dissolved stuff in it, which will change it a great deal. So I wouldn't put an awful lot of weight on this, but it will give you a general idea.
Well, thank you.
That is, I wouldn't guarantee that if you really put an antenna over, quote, fresh water, this is exactly what you would see. Okay, so what we've got to do here is go ground description. We right click this thing here, and now we go fresh water. We go okay, and we go plot that guy, and then we add the trace of the perfect of these. Oh, I didn't save the salt water. I saved the perfect ground. Okay, you remember the salt water and the perfect ground were almost exactly
Very, very close. I saw that.
except for the last few degrees. Okay, so there's quite a significant difference here. The fresh water has a very high dielectric constant, but it doesn't have very much conductivity, as it turns out. But that's what the dissolved solids are going to do. If you got if you got a swampy area, for example, I would bet that salt water would probably be a better approximation.
Yeah, every summer I try to rig a dipole directly over a little branch of a lake. It seems to make a difference, but not significant.
It won't help you putting it directly over it. What you need to do is have that lake out there where your reflection's taking place from the ground, which can be quite a long distance away.
Well, the lake's 32 miles long, so that's a start.
Okay, so you got it in that direction. All right. Back.
Thank you. Appreciate it.
You bet. So I get back to meeting. Okay, I'm back.
Can I ask something? Can you hear me?
By all means, go ahead.
Can you hear me?
Yes.
Yep.
Yeah, okay. So I guess the classical understanding is that the dipole is a full half wavelength antenna, whereas the vertical is a quarter wavelength, and the radios or the ground is supposed to produce the missing second half of the antenna. So I guess in theory, the pattern of the vertical should be the same as the pattern of a dipole, just flipped up 90 degrees. So if you flip your dipole up vertically 90 degrees, it should really match very much what the vertical does. They're really not all that different as far as I understand. The only disadvantage of the dipole, when you have a vertical, you have to put all these radios, have to go through a lot of effort and worry about your ground. quality and so on. But with the dipole, you have all that in the second half of your wire. Just one single wire gives you a perfect antenna with no, there's no, unoptimalities there. It's just really totally optimized. The only disadvantage is that it's not omnidirectional. I think that's the only disadvantage. Otherwise, the dipole is pretty much as perfect as you can get. Is that correct?
No. Let me try to explain a little more here. I'm going to divert just a moment here and tell Harry and you about something that happened to me quite a few years ago. I was invited to speak at a local radio club, and this was back in the days where it was all on transparencies with an overhead projector. And I got to the meeting, and the guy didn't have, the guy that was supposed to bring the overhead projector forgot to bring it. And so I said, well, do you have a flipboard or something? And well, no, they didn't have that either. Well, do you have a blackboard or whiteboard? No, they didn't have that. So I said, okay, what I'll do is I'll stand in front of here and I will answer questions about antennas for an hour. And I did that, and it was a real hit. And I've done that quite a few other times when a speaker didn't show up or something. I said, oh, I'll just stand up and answer questions about antennas. And I will be glad to do that. I call it my antenna Q&A. And sometime I'll be glad to do that, because the questions that you ask bring on more questions that I can answer, but they take some time. I'll give you a couple of very brief answers. One thing that I can demonstrate with EZNEC very easily is you worry about one of them being a quarter wavelength and one of them being a half wavelength, and therefore it'll radiate more or radiate less or something. And the first thing to remember is the law of conservation of energy, which says if you put 100 watts into an antenna, 100 watts comes out. And it doesn't matter if it's a quarter wavelength, a half wavelength, or a hundredth of a wavelength. And I can show with EZNEC, I can model, this is part of another lecture I usually do, my antenna basics lecture, that the hundredth of a wavelength dipole produces almost exactly the same pattern and gain as the half wavelength lossless dipole. And the only difference is a slight difference in pattern shape, which results in about a half dB difference in maximum gain. And the reason for that's a different shape of the current distribution. But those are lossless antennas. And in reality, your short antenna is going to be much, much, much less efficient. You're going to have a lot of resistive loss. And there's a couple of reasons for that. One of them is that your current in that little teeny short antenna will be very, very much larger than in the full half wavelength antenna. And therefore the I²R loss of the wire itself becomes important. The other one is that if you want to get some power to it from your transmitter, you've got to affect an impedance match somehow. And you'll find that the short antenna may have thousands of ohms of reactance. So you've got to get rid of capacitive reactance. You've got to get rid of with an inductor. And the inductor is going to have a lot of resistive loss. And those are the reasons that the short antenna doesn't radiate as much as the full half wavelength dipole. It doesn't have anything to do with the length of the radiator. Again, you put the 100 watts in, 100 watts comes out. In this case, most of it comes out in the form of heat in the small antenna and radiation in a large antenna. But anyway, the quarter wavelength antenna vertical versus a half wavelength antenna in free space. You can model both of those. This is, again, something that would take up a little time to do and could easily be done with EZNEC, even the demo program. Model a vertical over perfect ground as I did, and then model a dipole in free space. And you'll find that the patterns are identical, except for, of course, the vertical's only got half the pattern because you got a ground plane covering up the other half. You'll also find that the gain of the vertical is 3 dB greater than that of the dipole. And the reason for that is the fact that you're concentrating all of the energy in half of the space. The vertical is only radiating in a hemisphere, whereas the dipole in free space is radiating in a whole sphere. So those are some basic principles. And now what we have in the comparison between the dipole, a quarter wavelength high, and the vertical that I showed you, which is a quarter wavelength high, there are several things going on there. One of them is that the absorption of this low angle radiation is much greater for the vertically polarized wave coming out of the vertical than it is off the horizontal. The horizontal antenna has horizontally polarized radiation that bounces off the ground with very little loss. The vertically polarized radiation induces current in the ground, which is dissipated because the ground is resistive, except unless you get really highly conductive ground like salt water or perfect ground. And so there are a lot of complex things going along, and the simple explanation you gave is too simple. And again, you can use EZNEC to better understand some of these several things that are going on. I hope I answered your question. It may sound like I've avoided it, but I've tried to answer it as best I can.
Okay, I appreciate it.
Anybody else? I will take that to mean no one else has any other questions for you, Roy.
I hope my answer to Barry wasn't too intimidating. Didn't mean to scare people off, but this is, you know, antenna operation is both simple and complex. The simplest things are the principles, like what makes it radiate and so forth, are really quite simple. But once you get into talking about ground reflections, different polarizations and so forth, you have to take these things into consideration in order to understand what's really going on.
Okay, one last try. Does anyone else have any other question?
You got somebody in the middle there, John.
Speak up.
John is raising his hand.
I think
Go
he
ahead,
has
John.
he has to
Unmute and
unmute.
speak up.
Can you hear me?
Yes,
now
go
you can.
ahead.
Yeah, just a quick one, Brian. I really enjoyed that last explanation. Thank you very much. Do you have any Q&A sessions that are scheduled or anything like that where you know, people can take advantage of that?
No, I don't. You can set me up and I could try to do this again for you or for another group, and I'd be glad to.
Okay, thank you very much. It was very interesting. The whole presentation. Thank you.
Good. I'm glad you liked it. Thank you very much.
Okay, does anyone else have any further questions? Hearing nothing, I will thank you, Roy, for a very interesting presentation.